Okay, let's just dive right into this. Welcome to an explainer that traces a seriously fascinating journey. We're looking at how a highly theoretical mathematical sequence actually steps in to solve a massive, real-world bottleneck in computer science. We're going to start with a seemingly simple, but surprisingly highly contested question about generating numbers and see exactly how the physical limits of computation lead us straight to one of the most elegant, rule-breaking data structures ever invented. It's literally a story where pure mathematics crashes head first into the messy reality of physical computing hardware.
So here's our roadmap for today. First, we'll myth-bust a fiery Reddit debate about algorithm speeds. Then, we'll see why graph algorithms are so absolutely desperate for speed, identify the exact bottleneck that's slowing them down, introduce our hero, the Fibonacci heap, and finally, reveal the profound mathematical connection that makes this whole thing work.
All right, part 1, the fast Fibonacci debate, sparked by some pretty intense arguments over on the r/compsci subreddit.
Now, we all know the Fibonacci sequence, right? You just add the two previous numbers to get the next one. Simple. But how fast can a computer actually find, say, the 1 millionth number in that sequence? A user named Steno Dow claimed there's an O1 or constant time formula for this. Meanwhile, another user, Ryan McGady6, chimed in asking how to implement Binet's formula in Python without running into massive rounding issues. Sounds like a straightforward problem, just plug the numbers in, right?
Well, this brings up a really fascinating clash between pure math and computer science. Because while Binet's formula looks like it gives you O of 1 or O of log n time theoretically on a whiteboard, in practice, it's a totally different story. Taking massive exponents requires floating point arithmetic. And inside a physical machine, dealing with those endless decimals carries some massive computational overhead. Every bit of precision you demand eats up memory and processing power. Actually doing it this way is often way slower than just using textbook dynamic programming with memoization, which just adds the numbers up step by step. And this brilliantly illustrates the reality of the situation. As user Hextree pointed out in that thread, assuming multiplications take O of 1 time completely ignores the sheer volume of digits being generated. The nth Fibonacci number has an enormous amount of digits. Simply writing those digits to memory takes physical time. You literally break the rules of Turing computation if you claim it happens instantly, because a Turing machine still has to move its tape to write out every single digit of the result. So, if generating the sequence itself has strict theoretical speed limits, is it all just a mathematical curiosity?
Not even close. Let's move into part 2 and look at why graph algorithms need speed. Where does this famous sequence actually provide optimal performance out in the real world?
To answer that, we really have to look at graph algorithms. Think of the famous ones like Dijkstra's or Prim's algorithms. These map out shortest paths. Basically, it's what your GPS uses to calculate the fastest route home. And to do this efficiently, they rely heavily on a data structure called a priority queue. This ensures the algorithm always processes the closest, most optimal node next. Because otherwise, your GPS would map out routes through every random dead-end street in your entire city before finally finding the highway. The queue keeps the search laser-focused.
Now, as these routing algorithms explore a map, they frequently discover shortcuts. And when they do, the system has to be updated. For this, they rely on an incredibly specific operation within the priority queue called decrease key. It basically means taking a node you already know about and giving it a better, lower priority, or in our GPS analogy, a shorter distance. So if you thought a route was going to take 20 minutes, but you find a shortcut that makes it 10, use decrease key to bump that route way up in your priority list.
Which brings us to part 3, the decrease key bottleneck, and how this single operation is practically slowing down routing systems.
The math of graph traversal is honestly pretty unforgiving. Dijkstra's algorithm requires O of n total n queues to add points to the queue, O of n total extract mins to pull the closest points out, and crucially, it can require up to O of m total decrease keys. Here, m is the number of edges or roads in our map. And since maps have vastly more roads than intersections, that decrease key operation isn't just happening every once in a while, it is happening constantly. It drags down the entire system because every single time a new faster path is found, the system has to pause and reorganize itself.
Let's consider standard data structures for a second. In a typical binary heap, decrease key takes O log n time. The algorithm has to bubble the changed value up the tree to keep everything perfectly in order. Even if we upgrade to a lazy binomial heap where throwing new things into the queue becomes instant, O1, that pesky decrease key operation still takes amortized O log n time. Multiply that by m roads, and Dijkstra's absolute best overall runtime is capped at OM log n. This operation is literally the speed limit holding back our algorithm.
So, we clearly need a data structure that drops the cost of decreased key without totally ruining the speed of our other operations. Enter Part 4, the Fibonacci heap.
The amortized runtimes here are just wild. A Fibonacci heap miraculously achieves an amortized O of 1, meaning constant time, for that exact decrease key operation. Because it turns that massive O of m log n multiplier into just O of m, it pushes the total algorithm cost down to a highly optimal O of m plus n log n. For a comparison-based priority queue in Dijkstra's or Prim's algorithm, this is theoretically perfect. It is the absolute holy grail of graph routing efficiency.
But how in the world does it actually do this? Well, it allows for some highly structured messiness. A standard binomial heap demands perfectly ordered, rigid trees. If you decrease a key there, you have to spend all this time fixing the whole tree to keep it pristine. But a Fibonacci heap, it allows trees to get somewhat damaged and imbalanced. When we decrease a key, we just cut the node out and dump it in the root list. We save a ton of time by simply not cleaning up immediately. It's kind of like shoving all your clutter into a closet right before guests arrive. The mess is still technically there, but you've dealt with the immediate problem instantly.
Now, if you never clean your room, eventually you won't be able to find anything. If these trees get too damaged, our later operations are going to take way too long. So the Fibonacci heap institutes this genius lazy damage rule. A node can safely lose one child to a decreased key cut, and we simply leave a little mark on it, kind of like a warning. But if a marked node loses a second child, we immediately cut it from its parent too and dump it into the root list. This cascading cut slowly propagates information up the tree, which prevents the structure from degrading into a flat, useless list. It's this incredible balancing act between chaotic speed and structural integrity. Okay, moving to Part 5, the golden ratio connection. Let's see how this all circles back to our original mathematical debate and how this specific damage rule actually connects to the sequence. When you enforce the rule that a node can only lose one child before being cut, you are mathematically limiting how skinny or damaged a tree can get relative to its height. And when you calculate the absolute minimum number of nodes required to support a tree of order k under these specific damage rules, it turns out to be exactly the k plus 2 Fibonacci number. The maximum sizes of these damaged trees are strictly bound by the sequence itself.
So the crucial takeaway here is this. Because the structure maps directly to the Fibonacci sequence, it means the number of nodes inside these trees grows exponentially with the golden ratio, phi. This pure mathematical property guarantees that even at maximum damage, the trees remain dense enough that our extract min operation stays lightning fast. The algorithm achieves its optimal speed not by blindly calculating massive Fibonacci numbers, but by architecting a physical data structure that's natively governed by them.
You know, the Reddit debate was actually right to question the physical limits of calculating the sequence directly. But by embracing the structural mathematics of the Fibonacci sequence, we bypass the limits of standard computation entirely and solve one of graph theory's biggest bottlenecks, which really makes you wonder, as we hit the physical limits of modern computing, what other pure mathematical concepts are just waiting to be translated into the next great software optimization? Thanks so much for joining me on this explainer.